Hi everyone, I'm going to be working on some power electronic homeworks, and this is for question number one. Um, so let's get to it. For this question, it's for part A. It's asking us to find the Fourier series expression for the V bridge, which is the voltage across these two nodes. Let's just label them A and B. We do know that V bridge looks like this. And every time before we solve anything about a square waveform or any type of waveform, we want to know the characteristics, and that really helps us find the Fourier series expression easier. So what we're going to do is first write out what the Fourier series expression looks like for a typical waveform. So it would be something like f of t is equal to e naught divided by 2 plus infinite sum from n equal to 1 to infinity of a sub n times sine of n omega naught t plus b sub n cosine of n omega naught t. And now looking at the expression or the waveform right here, we're going to figure out what the characteristics should look like, and then we're going to actually find this. So first of all, we're going to look for if it's an even or odd function. So if we look right here, you can see that it's an odd function because we know if we start from here, we look to the right, we can see that it's mirrored and flipped. So we have phi 2 like p as a positive VDC, and right here we have the same thing, phi 2 almost 2 pi minus p right here. So this is also pi minus p, and 2 pi, since we start from pi, we just replace with 3. You see they're both mirrored and flipped, so we know that it's an odd function. So when it's an odd function, we know that the cosine is an even function, so it doesn't have any cosine. So that is equal to 0. Now let me get rid of all of these so I can explain one more property. Another property that I'm going to explain is halfway symmetry. And when a function is halfway symmetric, um, it's symmetric by half of its waveform. So let's see, if I draw a function like this, for the drawings. So this is t 0, this is t over 2. That means if a function is halfway symmetric, f of t is minus x of t over 2 minus t. So let's say we pick a point. Let's use this color right here. So basically, let me do this. This is a half a wave. And then if I take this, that's f of t, and then come back up here, right? That is, I came back by t over t. right? And then what I'm going to do is subtract t from it, so that's right where it should be. And then I'm going to go down by negative x, so I'm going to take the negative of this value, which is this much right here. I'm going to go by that value as negative and see if these two values are equal. You'll see that they both start, they're coming back up this much and this much, so these two values are equal. So we can say this is halfway symmetric. And when a function is halfway symmetric, the a of 2n from the sign is equal to b of 2n. Let me just change this to k. K is equal to 0 for all k element of n. N is going to be a range of 1 to infinity. So now we know something else too. That means the Fourier series for this function is going to look something like this. F of t is equal to n equal to 1 to all odd n's to infinity. It's going to be s of n times sine of n omega naught t. So it should look something that is very close to this. Okay, so now that we got here, let's go forward with finding s of n, an expression for that. Then from there we go on to find what the bridge should look like, the expression for that. So let me add another page, or maybe you could just fit it in here. Yeah, I'm gonna go with the new page. All right, so find a sub n. The expression for a sub n is equal to 2 over t, an integral over 1 period t of f of t multiplied by sine of n omega naught t d omega naught t. So now for us, we know that t is equal to 2 pi. So also looking back at this function, if I'm going to take the integral from here to here, I know that this is the same thing as this one. It's fully symmetric, so I don't really need to do anything. So all I'm going to do is do this integration from 0 to pi and multiply it by 2. That should give me this integration fully. So coming back right here, I'm going to rewrite the a sub n is equal to 2 over 2 pi from 0 to pi, right? So 2 over 2 pi. I'm just going to multiply it by 2, as I said. So I'm going to put 2 right here. And then let's look at f of t in that region. F of t is equal to VDC. What happened? It's equal to VDC from sig delta to pi minus delta. In that range, it's equal to just VDC. And let's go back right here. Actually, I'm going to change these back properly to delta to pi minus delta. and we figured out what t would be in that range. It would be just VDC. Then still gonna have sine of n omega naught t d omega t omega t. Okay, so I can factor out the VDC out of there. So x of n is equal to, taking it out, I'm just going to get, I'm going to cancel this 2 with this 2, and then I'm going to have 2 VDC over pi. And now I'm just going right here, I'm left with sigma to pi minus sigma of sine of omega naught t d omega naught t. So taking that integral, I know that's just going to become 1 over n. Just take out the 1 right here times cosine of n omega naught t evaluated between pi minus sigma and sigma. So s of n is equal to 2 VDC divided by pi multiplied by minus 1 over n multiplied by what is cosine of this expression actually evaluates. So let me simplify first in this step. Becomes cosine of pi minus sigma minus cosine of sigma. So what this gives me is, if you evaluate these two based on the trigonometry, what this becomes is just cosine, it's really negative cosine of sigma. So when we multiply this negative by this negative, I'm just going to write it down. Actually, 2 right here. Sorry for that. This becomes 2 minus 2 times cosine of sigma. Write it down, minus 2 cosine of delta. Nothing with these names. Okay, so then s of n, this is going to be equal to what? 4 VDC divided by pi. And give some room right here so I can write cosine of delta. Okay. Yeah, forgot n. And it comes right there. So now we find that h of n is equal to that. Now we're going to rewrite this expression that we found up there, f of t, by plugging in that h of n. So the expression for this becomes, and remember n is odd, so I'm just going to replace n with n is equal to 2m plus 1 to make it just an odd number. Now I'm going to write down that v bridge is equal to, v bridge is equal to, can put these outside as well. So yeah, let's just put that 4 VDC times cosine of sigma whole thing divided by pi and then is m from 0 to infinity, because it's all odd numbers. Now, want to put the n inside, so 1 over 2n plus 1, which was 1 over n in that case. And then I'm going to have multiplied by sine of, initially we had this as n omega naught t, but we replaced n with 2n plus 1, so I'm just going to make this bracket, so then a lot of mistakes. 2n plus 1 omega naught t, and that is going to be my V bridge expression for the transform, obviously. Yeah, so we're done with part A. Just to recap, we looked at the waveform right there. We looked at how the series should look like. We found out it was odd, so all the cosine terms went away. We found it was halfway symmetric, so all the even coefficient terms are going to be equal to 0. So we just found out it's just going to be all odds. Then we found out, so since cosine terms cancel out, we just have the sine terms going on in there, and then we just found out the expression for a of n, which is this expression going forward, solved it, then plug that in instead of plug a sub n into this expression, which is v bridge is is actually v bridge. And we found out this is the expression. I'm going to do actually is going to clean up some of this, which is not necessary to have. So delete. I'm just going to write down right here that this is